Let's jump right into this explainer. You know those massive cart-based ultrasound machines, right? The ones with so many buttons they look like they require a pilot's license to operate? Well, we are moving way beyond that. Medical imaging is undergoing a profound, almost magical transformation. We are shifting toward pocket-sized, battery-powered, software-defined smart probes. Today, we're decoding that transformation, looking under the hood at the incredible engineering leaps that make this possible, from the microscopic sensors touching the skin all the way to the artificial intelligence reconstructing the final image.
To understand how this works, we're going to follow a sound wave right down the data pipeline. Here's our agenda. We'll start with the smart probe revolution, then dig into PMUT and CMUT transducer tech, check out how we're miniaturizing high-voltage power, weigh the FPGA versus GPU architecture debate, and finally wrap up with AI-driven beamforming.
Section 1. The Smart Probe Revolution. Before we start shrinking everything down to fit in your pocket, let's quickly establish our baseline.
Okay, let's dive into this. Here's your standard ultrasound transmission and reception block diagram. It starts with a transmit pulsar, sending an electrical signal into the transmit-receive, or TX/RX, switch. That switch then sends high-voltage pulses to the actual probe to generate the sound waves. Then, when echoes bounce back from the body's tissues, that exact same switch routes those faint, tiny analog signals through amplifiers and right into an analog-to-digital converter, or ADC. Traditionally, all of this hardware, the pulsars, receivers, fast ADCs, took up huge, massive circuit boards. The big challenge today is figuring out how to cram all of that power-hungry, complex hardware into something you can literally hold in your hand.
Section 2, PMUT and CMUT transducer tech. Let's talk about the physical interface with the human body itself.
For decades, we relied on bulky piezoelectric crystals, cut with physical saws. To shrink the system, we have to ditch the crystals and enter the world of micro-electromechanical systems. Enter micro-machined ultrasound transducers, or MUTs. Instead of cutting crystals, we're now using the exact same photolithography and microfabrication techniques that build computer chips. We are laying down extremely thin films on silicon substrates. And this is a massive deal because it allows for unbelievable miniaturization. We can now monolithically integrate thousands of sensors directly alongside the CMOS control electronics on the exact same piece of silicon. It's quite literally ultrasound on a chip.
Now, what's really interesting about this is how the physics actually works. Take a look at the cross-section of this capacitive mute, a CMUT. There's a physical air gap cavity built right into the silicon substrate, with a flexible membrane suspended over it. When you apply an alternating voltage, electrostatic forces literally pull that membrane down. It vibrates, and boom, you've got a sound wave. And it works in reverse too. An acoustic echo hits the membrane, deflects it, changes the capacitance of the gap, and we measure that as our received signal. It's an incredibly elegant physical mechanism etched on a microscopic scale.
But CMUT isn't the only option. We also have PMUT, or Piezoelectric Micromachined Ultrasound Transducers. The industry actively debates which is better, and really, it comes down to engineering trade-offs. PMUT uses piezoelectric thin films bending in a flexural mode. That gives it a lower electrical impedance, which is fantastic because it means simpler drive electronics and lower power consumption. On the flip side, CMUT, using that electrostatic air gap, generally gives you a broader operational bandwidth for better image resolution and superior pitch scaling so you can pack more sensors into a tighter space without crosstalk. Both are absolute game changers over old ceramic crystals.
Section 3, miniaturizing high-voltage power. So, we've got microscopic transducers. But to generate sound waves that can actually penetrate deep into the human body, they still need a serious electrical kick. Which brings up a question that probably keeps electrical engineers awake at night. How do you safely pack up to plus or minus 80 volts into a 5mm space? Remember, a smart probe is totally handheld. We are fighting a severe uphill battle against crazy space constraints, noise immunity, and of course heat dissipation. I mean, you absolutely cannot have a device burning a patient's hand.
5 millimeters. That is the absolute maximum height limit inside these sleek probes. In the old cart-based machines, engineers would just use transformer-based flyback converters to step up the voltage. But transformers are bulky. You physically cannot fit them inside a 5mm gap. We need a completely new power topology to run off a standard low-voltage lithium-ion battery.
And that's where companies like Texas Instruments come in with the SEPIC topology. That stands for Single-Ended Primary Inductor Converter. By swapping out bulky transformers for uncoupled inductors, they can actually meet that strict 5mm limit. This setup efficiently takes low battery voltage and pumps out a programmable high voltage up to plus or minus 80 volts. And amazingly, it maintains up to 88% peak efficiency. That efficiency is absolutely crucial because less wasted energy means less heat cooking directly in the palm of the doctor's hand.
Section 4. FPGA versus GPU architectures. All right, we fired the pulse, received the tiny echoes, and digitized the signal. Now we track it away from the physical hardware and into the compute architecture. So the crucial point is how we actually process this absolute fire hose of digital data to form an image. This sparks the great hardware-software partitioning debate, FPGA versus GPU. Inside the battery-powered probe itself, field-programmable gate arrays, FPGAs, like the Xilinx Zinc, are favored. They offer unrivaled power efficiency and deterministic ultra-low latency. But if you transmit that raw data out of the probe to a high-end cart or the cloud, you can tap into GPUs, like NVIDIA RTX cards. GPUs give you the raw CUDA-powered muscle you need for incredibly complex, nonlinear beamforming algorithms that an FPGA just can't handle as easily. This shift to a software-defined architecture is a total game-changer. Historically, beamforming algorithms were locked into hardwired ASICs, application-specific integrated circuits. If you wanted a new feature, you had to fabricate an entirely new chip. Today, companies like Philips are transitioning their platforms to utilize NVIDIA GPUs. Because the pipeline is configurable in software, developers can constantly update algorithms. This raw compute power enables crazy feats, like capturing full 3D cardiac volumes at resolutions and frame rates we used to only see in 2D imaging. It instantly translates to faster, more accurate diagnoses because the algorithms can automatically adapt to a patient's unique acoustics.
Section 5. AI-driven ultrasound beamforming, the final leg of our journey. Translating raw, digitized RF data into a pristine diagnostic image.
Traditionally, standard algorithms used a mathematical process called delay and sum beamforming, but deep learning beamforming fundamentally rewrites the math. Instead of stepping through a rigid chain of computational signal processing, deep learning models bypass those intermediary steps entirely. They use neural networks to learn a direct mapping straight from the raw radio frequency data to the final high-quality image. And this brilliantly illustrates the elegance of the AI approach. Look at how simple this pipeline is. Step 1, you acquire the raw data. Step 2, feed it right into the neural network mapping. Step 3, instantly output a high-resolution image. Skipping the old, computationally heavy signal processing chain means AI-driven beamforming can drastically speed up real-time image formation.
But it's way more than just raw speed. It's about clinical confidence. AI models trained on massive datasets are incredibly good at suppressing speckle, that grainy noise you constantly see in ultrasound images. They automatically enhance edges, boost contrast, and resolve deeper targets. More importantly, they reduce patient-to-patient variability. So no matter the patient's specific anatomy, the sonographer gets a robust, highly reliable image every single time, making diagnoses far more confident. Which leaves us with a truly fascinating question to ponder. We've traced the evolution from bulky crystals and analog boards to micro-machine silicon sensors, software-defined GPUs, and artificial intelligence. Ultrasound is no longer just a physical hardware challenge. It's rapidly becoming a purely computational one. As our compute power and AI models continue to scale exponentially, what limits what we can ultimately see inside the human body? The possibilities here are just staggering. Thank you for joining me on this explainer. Keep asking those big questions, and I'll catch you next time.